Right, so let's take a look at Chapter 5. So in Chapter 5, we're going to study the last two types of functions before we start trig. In 5.1, we look at what's called exponential functions. And then in 5.4 and the next section, we look at kind of the opposite of these functions, which is called logarithms. So anytime we study functions in math, there's always a function that's the opposite of it. Like if you square something, the opposite is square root. If you cube something, cube root. If you have an exponential, the opposite is a logarithm. So that's why we're going to look at these two together this week. Right, so first I just want to compare those two, x to the second and 2 to the x. Does anyone remember the name of the number that you write lower, like this thing? And then this also has a name as well. What's the name of the number you write that's lower?
Constant.
It could be a constant. Sometimes it's a constant, sometimes it's a variable. Just remember the number that's lower than the higher number? No? Anyone remember what the higher number is called? Yeah? A superscript? Yeah, you could call it that, or it's also...
The radicand?
Not the radicand. That would be the thing under a root. So roots, we're all done with roots for now. Yep.
Coefficient?
Think like a basic name.
Base?
Exponent. Yeah, and the other thing, you just said it.
Coefficient?
Nope, I think you said after that. The base. So in each case here, you have a base and an exponent. You can call an exponent a superscript, but generally you just call it an exponent. Okay, the difference is that in one case, your exponent is a variable. In the other case, it's a constant. And that'll basically tell you whether or not you have an exponential function. Okay, so in the one on the left, x squared, the base is x, the exponent is a 2. The one on the right, we've switched it around. The base is 2, now that's the constant, and the exponent is an x. Does anybody have a guess which one of these would curve up faster? 2 to the x. It's going to go up much, much faster than x squared. Think about if x was 10. If you do 10 to the second power, that's 100. If you do 2 to the, what did I pick here for x, 10? If you do 2 to the 10th, that's a lot bigger than 100. It's 2 times 2 times 2, 10 times. All right, so 2 to the x will go up much, much faster. In fact, exponential functions are one of the quickest growing ones. Okay, they curve up very quickly, and they almost appear to go vertical. They're never quite vertical, but they're very steep. Okay, so the one on the left is an example of a polynomial. When you have the base as a variable and the exponent as a non-negative integer. So in other words, the exponent can't be a fraction. It has to be 1 or higher. That's called a polynomial. X squared, 3x cubed, 5x to the 5th minus 7x squared. All those things I just said, those are all polynomials. Now, once you make the exponent the variable, that's when you start to get into exponentials. Okay, so now with an exponential, you've put the variable up in the exponent, and the base has to be a positive real number, but not 1. So variable as an exponent, base is a positive real number not equal to 1. Anybody know why not equal to 1? How come that wouldn't be considered an exponential? 1 to the x. Yeah?
No matter what x is, it's always going to be 1.
Yeah, it's not growing. No matter what x is, it's always 1. Okay? If you make it even just a little bigger than 1, 1.1, now it's exponential. And there's two kinds of exponential. There's exponential growth, which means it goes up very quickly. Does anybody know the name of the one that goes down? Decay. Yep. And whether or not you have growth or decay, that's all controlled by the base. We'll talk about how you figure that out. Any questions on the definition of an exponential function? Exponent's a variable. Base is a number positive number other than 1. So with exponential functions, just to show you a picture, just graph 2 to the x. Okay, you can see it's tracing right on the axis, so it's a little hard to see, but it is tracing on the x-axis. It goes left forever, and it goes right forever. Okay, the reason? If you take 2, and I asked you what numbers can you raise this 2 to, can you raise the number 2 to? You can raise it to any number you want. You can raise 2 to a positive number. You can raise 2 to a negative number, fractions, decimals, or 0. So there's no limit for the domain. It's all real numbers. And again, that domain is dependent on the condition I just told you, that your base is a positive real number, not equal to 1. If you change that condition, we're not dealing with exponentials anymore. Okay? So we want to make sure that that's always true. Okay, how about the range there? Have a guess what the range would be?
Zero to infinity?
Yeah, it's 0 to infinity. Do you think it ever reaches 0?
Yeah. No.
No, it'll never reach it. Because remember what a negative exponent means. Negative exponent means you flip. So you write it this way. So in that case, 2 to the negative third is 1/8. It's a small number, but it's not 0. If you did 2 to the negative 10th, that would mean this. Take 1 divided by 2 to the 10th power. Very, very small. But is it going to equal 0? No, it's not going to equal 0. All right, so the further and further left you go, the closer and closer and closer your y value gets to 0. How about the further and further right you go? What happens to your y value there? And what does it approach?
Infinity.
Infinity. It just goes up forever. If you had a decay function, that would be just the opposite. It would come down, and everything we just said would be reversed. Okay, so these are all examples of exponential functions. (10 to the x, 4 to the v, pi to the x). They all have variables in the exponents. They all have bases that are positive and not equal to 1. Below are all things that are not exponential functions. X cubed, that's a polynomial. Your exponent is a non-negative integer, and your base is the variable. That's f of x. G of x is pretty much the same thing. That's a polynomial. The last one, well, it's a combination of a radical and a polynomial in the bottom. But either way, you don't have any exponents in the bottom 3 that are variables. So those are non-exponential functions. Okay. Does anybody have a question like, well, what if I had this, like this to this? Would that be exponential or not exponential? How about if I had x to the x? Would that be exponential or not? Well, does it have a variable as an exponent?
One. Wouldn't one be the next?
Well, just the way I wrote it, is there a variable as the exponent?
Yeah.
Yes. What's the base?
X.
It's x. We don't know what the base is.
But that could be negative.
It could be negative. It could be anything.
So next.
So that's not exponential. The base has to be a fixed number. 2, 1/2, 7.4. Okay, it can't. The base can't be a variable. Okay. So that's not exponential.
Can you go back a little bit?
All right, so let's graph 2 to the x and 3 to the x. Which one of those do you think is going to curve up quicker?
3 to the X.
Yeah. 3 to the x is going to curve up quicker. Okay, let's just graph them both, and I'll put a picture so you can see it. Okay, I already have 2 to the x. 3 to the x. Okay, they both look the same as you go to the left. They're kind of getting closer and closer to 0. But after you cross the y-axis, you can see that 3 to the x starts curving up quicker. And they cross each other right at the point 0, 1. So that's an important point for any exponential. Any exponential function, if you don't shift it or stretch it, okay, if you don't do anything to it, it'll always go through the point 0, 1. Always. Okay, because anything to the 0 power, it doesn't matter what it is, anything to the 0 power is always 1. All right, so the next part, I'm just going to remind you a little bit about negative exponents and how we can deal with that. When we're comparing two graphs, generally we don't want negative exponents. Negative exponents is just going to confuse us. So I'm going to show you how you get rid of them. So anytime you have a negative exponent, what you do is you take and put that expression in the bottom of a fraction, and it becomes positive. Right? So if you had something like a to the negative third, you could make it 1 over a cubed. Okay, so taking a negative exponent, putting it in the bottom of a fraction makes it positive. So let's see, we're going to use that idea to simplify an exponential expression with a negative exponent. Okay, what I'm going to do is turn this negative into a positive somehow. Okay, even though I haven't written it, what number is in front of
1.
the exponent there?
1.
Yeah, in this case it's actually a negative 1x. Okay, negative 1x, negative x, same thing. What operation am I doing with the negative 1 and the x? We're multiplying. Okay. Does anybody remember the rule when you multiply exponents together? When does that happen? When the bases are the same, you add exponents. So if you had like 2 cubed times 2 to the 5th, that would give you 2 to the 8th. You do 3 plus 5.
Parentheses.
Can you give me an example?
Like 2 to the 3rd, and then outside the parentheses there's like a 5.
Yes. So when you have a power raised to another power, that's when you would end up, bless you, multiplying your exponents. So let's think of it that way. A to the negative x, it's really a to the negative 1 times x. Why would you do negative 1 times x? Because it's a power to a power. Negative 1 to the x means negative 1 times x. And now this part right here, we just simplified right there. So a to the negative 1, you can rewrite it as 1 over a. So this little shortcut, we don't have to go through the explanation every time, but the point is anytime you have a negative exponent, if you want to get rid of the negative, take the base and flip it, and it makes the exponent positive. So if I had 2 to the negative x, and I wanted to write that with a positive exponent, that's the base, flip it. And now you can write it as a positive. Okay, what about if I had 5 to the negative x? Can you rewrite that as a positive? Yeah?
It'd be 1/5 to the x power.
Yep. Okay, and I'll show you in a minute why you have to do that. But when we want to think about exponentials, it's a lot easier to think about it if the exponent is positive. We don't want anything. Okay, any questions on that idea? Okay. All right, so let's look at each of these graphs. Okay, we've got 2 to the x. And can someone tell me how to rewrite that one, 2 to the negative x? I'd like to write it with a positive exponent. Yeah, Josh?
1 over 2 squared
1 over 2
to the x.
to the x, yes. Now, if you know about growth and decay, which we will in a little bit, you can look at those and you can figure out which one is growth and which one is decay. It all has to do with how big the base is. Without rewriting it, it looks like the base is a 2 here. It's not. In g of x, the base really should be a 1/2. So let's graph them and see what they look like. Did you have a question?
I answered it myself.
All right. So 2 to the x, I already have that one. It doesn't matter how you type in g of x. Type it in as 2 to the negative x or 1/2 to the x. I don't care. You're going to get the same thing. Okay, so there's 2 to the x. Notice it's growing very rapidly as you go to the right. There's 1/2 to the x. It's decaying as you go to the right. Okay, so looking at those two graphs, we're going to summarize the domain and range of each one. Just to kind of make this clearer, 2 to the x is the blue graph. This one is the red graph. Okay, so I'll start with f of x, and then I'll ask you guys to help me with g of x. Okay, f of x, that's the blue one. The domain of the blue one, well, it's going to the left forever, and it's also going to keep going to the right forever. Okay, it starts to go up very steeply, but it's still going to the right. So the domain on the blue one is negative infinity to infinity. The range, we already talked about it. It's going from 0 up forever. But does it ever reach 0? No. So the range is 0 to infinity. Okay, that's for our f of x. Now how about g of x? How far does it look like the graph in red is going left and right?
Positive, negative.
Yeah, it's the same thing. In fact, we could actually prove it's a mirror image. The graph in red and blue are reflections of each other. So if something goes left and right forever, and you make a mirror image of it, it still goes left and right forever. Okay. How about on the red graph, up to down? What's the highest and lowest that one would go?
Infinity and 0.
It's the same thing. It's a mirror image.
So the opposite, right?
It's still 0 to infinity. You always put the small number first and big number second. Yeah. So the lowest the red graph goes is 0, never reaching it. The highest it goes up forever. And if you're not sure why it never reaches 0, you can always go to your table and focus on the red graph, ignore the blue column for now. But start plugging in bigger and bigger values for x. When x is 10, we get that. That's scientific notation. It's 9.7 times 10 to the negative 4th. Okay, so it's a small number. As you go even further, now we're at 3 times 10 to the negative 8th. That's even smaller. Okay, that's like 0.000000003. Very small number. All right, you can always double check on your table if you need to. All right, so now I want to see if we can generalize this idea, not just for the graph where 2 is the base, but where anything is the base. 3, 4, 5. It doesn't really matter. The answers would come out the same. So the key difference is going to be, are you looking at a base that's greater than 1? Or are you looking at a base that's a fraction, less than 1? Okay, let's start with f of x. That's the case where you have a base bigger than 1. As an example, the graph in blue is what I just did. Okay, but now pretend a could be anything. 3 to the x, 6 to the x, 12 to the x. Some number bigger than 1 to the x. Okay, in that kind of graph, if you have a base bigger than 1, it's going to look like the graph in blue. What happens as you head to the right for the graph in blue? What happens to the y value? It goes to infinity. And even though I'm only showing you 2 to the x here, that would work for anything. Anything to the x, as long as it's a number bigger than 1. Now, what happens with the same graph in blue as you head to the left? What does y get closer to in that case? It gets closer to 0. And what I'm basically summarizing here is the behavior of an exponential growth graph. Okay, any exponential growth graph always has that behavior. The second one is an exponential decay graph. That's where you have a fraction. What happens in a decay graph as you head to the right? What does your y value approach there? Yeah. In a decay graph, your y value approaches 0. What happens in a decay graph as you head to the left? The y value approaches infinity. Hey, any questions on that idea? The way a growth graph or a decay graph behaves. I haven't written those terms down yet, but I will, probably on the next page. Right, so let's write those terms down. So the key difference between the two graphs that we just looked at is, do you have a base greater than 1? That's exponential growth. Or is your base a fraction? Okay, between 0 and 1. That's exponential decay. Will you ever have a base that is negative? When we're talking about exponential functions. No, that's one of the very first things we said. The base has to be a positive number, not equal to 1. So what would happen if the base was negative? Don't worry about it. We're not going to do that. So your base is either greater than 1 or between 0 and 1. Okay, I'm not going to go through the whole explanation again, but transformations on these functions work exactly the same as transformations we've done all year. Your horizontal stuff is always inside the function, closest to x. Your vertical stuff is always on the outside. So this problem here, if I was going to convert it into like a homework problem from last night, would be just like this. Cube root of x plus 1 times 2 minus 5. That's how that problem would be written if it was a last night type of problem. Okay, so let's go through and see if we can figure out the transformations. Does everybody have what's on the left?
Yeah.
Okay, so 3 to the x, that's the basic function you're comparing g to the x to. Wyatt, could you tell me how many transformations are happening in g of x?
3.
Yep, exactly. We've got 3 transformations happening. Anybody know what number we're going to focus on first?
The 1.
Yep, I'm going to focus on that plus 1. Anyone else think they know what the plus 1 is going to do? Think about it. It's inside the function. So we talked about the stuff inside is either your horizontal or your vertical stuff.
You go to the right one.
Yep, it's a horizontal shift. I agree with that part. But which way is it going to shift? Yeah, it's left one.
It goes opposite.
Yep, it always goes the opposite for horizontal. So horizontal shift, left one. There's nothing else inside the parentheses, so we are done with horizontal stuff. The other thing you could have had would have been something like that. If you put a number inside next to x, that's a horizontal stretch. Okay, just like with square roots, same idea. The next thing we're going to look at is the 2. What's the 2 going to do? We know it's vertical, I said that, but is it a stretch or a shift?
Stretch.
It's a stretch. Okay. Shifts are always added or subtracted. Stretch is always multiplied. So vertical stretch, a factor of 2. And lastly, how about the minus 5?
Vertical shift
Shift which way?
to the left by 5.
Vertical shift to the left?
Oh no,
Think about that a little bit.
yeah, down.
Down. Yeah. So it's going to be shift down 5. So vertical shift down 5. Okay. Vertical does exactly what you would expect. Minus is down, plus is up. Horizontal, it's always backwards, and it has been all year. Okay. Any questions on that? What if I did that? What would that negative do? It would cause, yep, a reflection, and that would be a vertical reflection because it's with the number that does the vertical stuff. Vertical reflection is over which axis? X. I know it's a little tricky to think of it that way, but that's vertical, that's how it works. Good. All right. This graph, you don't have to graph it. I'm just going to graph it, and I want you to look at it because something kind of interesting happens here. It's not an exponential function. It does have a variable as an exponent, but the base is not fixed. The base can change because there's a letter in it. But let's just graph it. I want to show you what it looks like. So 1 plus 1 divided by x to the x. what does it look like you have in that graph? We've talked about this before, something that it gets closer and closer to but never reaches.
Asymptote.
Is that what you're going to say? Yeah. It's an asymptote. And the quick way to see what it is just type in big values for x. At 15, we're at 2.6. At 500, we've only gone up to 2.7. If you go all the way out to 50,000, it's still 2.7. It looks like it's this number 2.718, and it keeps going on after that. If you look in the negative direction, same thing. It's getting very close to this number 2.718. Anyone heard of that number before? Yeah? So that number 2.718, it's a special number, just like this symbol. That's a special number in math. Well, 2.718 is the letter E. So it looks like we have a horizontal asymptote at 2.718. It doesn't keep repeating 1828. The next number is different. I don't remember what it is, but it doesn't keep repeating like that. And that number is known as E. So the reason I'm showing it to you is because tomorrow, when we study logarithms, there are two logarithms that have special bases. This is one of them. And the special base is E. And that's called the natural logarithm. Other than that, that's all I'm going to say about E today. But I just wanted you to see that when you graph that function, you get a horizontal asymptote at a number we're going to study more tomorrow. Okay, people usually aren't as familiar with E because it's not used as much as pi, but it is used. Any questions on that? As far as a proof, like why does this graph approach 2.718? That's a harder question to answer. There is a reason why, but it's not something we're going to look at. All right, so the last two things we're going to look at are the formulas for growth and decay. The first example I'm going to give you is a problem where you start with an initial population, or it could be anything, an initial amount of something, and that amount is going to increase by the same rate every year, by the same percent. So you could do this for like a bank account. Let's say you had $500 and you make 2% interest every month. That's an exponential growth problem. It's a very slow exponential growth problem. You're not going to put $500 in a bank account and have your money just shoot up very quickly. It's an extremely slow curve up. And by the time your money really starts to make a lot of interest, I mean, you got to have millions of dollars by the time that curve goes up fast. It's a very, very slow curve. And that's the formula for exponential growth. There's three variables in it. P is your initial amount, whether it's a population or money or whatever it is. Okay. R is the rate of increase, but it has to be as a decimal. So could someone remind me if I had 5%? How do you change 5% to a decimal? Yep, Curtis.
Well, you just move the decimal over 20 times.
Yeah, you just move the decimal two places, and you get 0.05. If you had 12% as a decimal, it would be 0.12. So anytime you have a percent, you have to put it in as a decimal. And T, forgot to label that, T is the time. Now, in that formula, there's one thing you would have to change to make it a decay versus growth. Anybody know the one thing you would change? Yep.
Plus to or minus.
Yep. Change that plus to a minus, and now you turn it into a decay problem. I'm not going to relabel what all the variables are because you have them up above. So a decay problem might be something like you start with 1 million acres of forest, you chop down 2% every single year, never changing the amount, so always 2% for the next 30 years. How much is left? That's exponential decay. Okay, does everybody have the exponential growth and decay formula? All right. So let's look at this one. We have a town with a population of 50,000 people. The population of the town is going up 2.5% every year, and you're going to assume that never changes. If it changed, that complicates the problem. We'll just assume it stays the same growth rate. So first of all, I want to set up an equation that represents it. And then we're going to use our equation combined with the graphing calculator to figure out how long before the population of the town doubles. How long before we have 100,000 people in the town. And this is assuming that everybody that's born stays alive, the growth rate stays the same. We're not taking people away at the same time we're adding. That would be more realistic. It would also be a harder problem. Okay, so to write this as an exponential growth, what's the first thing I need to do?
Make the formula.
Yep, so I've got my amount of people as a function of time. Or you could do population as a function of time, P of t, however you want to write it. Okay, what's the first thing in the exponential growth?
50,000.
Yep, the initial amount. 50,000. And it's growth, so we know it's plus.
1 plus 2.5.
So 1 plus, and then what are we going to put after the plus sign? Yep,
0.025.
yep, we're going to change it to a decimal. To the t. That's it. That's our exponential growth formula. The only thing I could do is I could add 1 and 0.025 and put 1.025. Yes. Thank you. Okay. So now we've done the first part. Second part. We're going to use that graph to figure out when the population is 100,000. Where would I plug in the 100,000? For t or a of t? A of t, that's an amount. So plug that in right there. So basically I'd have 100,000 equals 50,000 times 1.025 to the t. So what I'll do is put that in y1, put all of that in y2, and then I'm going to see where these two graphs do what?
Cross.
Yeah, look for where they cross. Technically, it doesn't matter which one you put as y1, but just put one of them as y1, put the other one as y2. So 50,000, 1.025. And remember, in the calculator, you always use x as the variable. You can't use t. Now, the minimum amount of people we have is 50,000, and it's going to go up from there. So for my population, starting at -10 and going to 10 people, not enough. Let's start at 50,000 people. We want to know when it hits 100,000, but I wouldn't put it right on the edge of the screen. So maybe 120,000 would be good. Now, x is time. Are we predicting back in time? No, this model is used to predict from this point forward. So we can't use it to predict backwards. X max is how many years go by before we hit 100,000. Right now, we don't know that. I'm going to guess within 40 years, it'll be pretty close. If not, I'll make it bigger. Okay, so there's my 100,000. Here's my population. You can see it curving up. It is going to hit within 40 years. Exactly when? Do your intersect. It's going to take 28, a little over 28 years. So after, you could round that to about 28.1 years.
Wait, how'd you write in the equation 50,000 times 0.1?
Equation, just like that. That was a 1.
Mine's not working.
And you have to set the window too.
Yeah, I did that.
If anyone's isn't working, we can take a look after and see. Just leave what you have typed in right now and I'll come look at it. Question on that? So that's how you solve an exponential growth, at least on the calculator. Okay? Just calculate your intercept. It's 28.1 years. So as always, when you're setting your window up, be careful about including negatives. In this case, negative people don't make sense. In fact, even people under 50,000 doesn't make sense because our population's growing. So that's just something we've said all the time. All right, I'm going to show you the formula specifically for something doubling. Okay, doubling is a special kind of exponential growth. And I'm just going to show you the formula. So that's the formula for something doubling. Kind of starts off the same, initial amount, whatever that is. But if you're going to be doubling, your base is always a 2. It's not 1 plus r. You always put in a 2 for doubling. And then the exponent is t divided by the length of time to double. Now, we didn't have that division in the exponent before. Reason you need that is because let's say something doubled every 10 days. Something doubled every 10 days. After 10 days, how many times would it have doubled? If it doubles every 10 days, after 10 days it will have doubled once. So you would want your exponent to be the amount of days divided by the length of the time to double, 1. How about after 20 days? How many times would it have doubled? Twice. So you want your exponent to be a 2. 20 days divided by length of time to double, that'll give you a 2. Okay. So this one, I'm not going to solve it. I'm just going to set it up. Solving it would be just like the other problem. You've got 100 bacteria doubling every hour. So what does that mean? It doubles every how many hours if it's every hour? 1. So really in this case, the doubling period is 1. So you don't really need to divide by 1. But we'll write it. So it doubles every 1 hour. When will there be 350,000 bacteria? Okay, so first, can someone give me a formula that would represent the amount of bacteria I have as a function of time? What would we start with? Yep, Ian.
100.
Start with your initial amount. Yep.
Times 2.
We're going to do times 2 because we're talking about a doubling problem.
And 2 to the whatever hour.
Yeah, 2 to the time divided by the length of time to double is just 1. Now, if you were going to solve it, where would the 350,000 go? B of t. Okay, so there's the first part of the problem. Second part, put that in y1. Put that in y2. See where they cross. Okay, you might think it's going to take a while, but actually if it's 100 bacteria doubling every hour, that's going to hit 350,000 pretty quickly. Probably within a day, I would think. Okay. And then the last formula we're going to look at is a decay one. Okay? It's the opposite of doubling. Does anybody know what that's called if something keeps getting cut in half over and over? It's, sometimes they talk about this with like nuclear waste. It has a certain blank to it.
Like a half-life?
Half-life, yep, half-life. So the formula is pretty much the same as doubling, except the base is a half instead of 2. But if you don't understand what half-life is, basically, simple way to explain it, if you have 100 pounds of nuclear waste and the half-life was a day, after 1 day, you'll have 50 pounds left. Half of it will just evaporate or whatever. After another day, half of that would be gone, so you'd be down to 25 pounds. After another day, half of that. So technically, it's never really gone because you just keep taking half and half and half. It gets very, very small, but it's always still there. Medications have the same thing. Okay, when you take a medication, there's a half-life to it. So maybe the medication's half-life is 6 hours. So if you take a 10 milligram pill in the morning, 6 hours later, only half of it is left in your system. 6 hours later, only half of that. So medications have half-lives as well. Yeah?
Yeah, that's what I was going to ask.
Yeah. Usually what complicates a medication problem is you keep taking more of it. So it's not, like if you just took one pill, eventually it would be a very small amount in your system. But as you keep taking, let's say you take a pill every 12 hours, you keep introducing more. So at some point though, it levels up. The amount of medication in your system, it stabilizes. It's kind of crazy at first, but then it smooths out. Okay. So let's just see if we can set up a half-life problem. Okay, so this says a certain substance has a half-life of 20 days. You're starting out with 5 grams. Okay, let's write that as an equation. What's my initial amount here? 5. When we're doing a half-life problem, the base is always 1/2. And what's my exponent here?
20 divided by whatever. No. T divided by.
Yes, t divided by 20. Because if 40 days have gone by, that's 2 half-life periods. I want my exponent to be a 2. If 80 days have gone by, that's 4 half-life periods. Okay. There's your equation. And now it asks, when would you have less than 1 gram? Just to show you kind of how it would work, you type in on the calculator what's on the right. You're going to get a picture that looks like that. It's going to decay. Put in a line at 1. And then you would see where those 2 lines do what? Where they intersect. So it would be any point from that time on, you would have less than 1 gram. So any point from there forward in time. All right, so homework tonight, it's on 268. 4 through 7, 19, 25, 27, 31, 35, 47 to 49, and 57. Okay, so we'll take a look at that first thing tomorrow. Don't forget my extra help will be tomorrow instead of Thursday because of parent-teacher conferences.